The broadcast is now starting. All attendees are in listen-only mode.
Hello, welcome to Coffee with Caleffi. Thanks everybody for joining us today. I'm proud to welcome two of my colleagues, Kevin and Jody. You may have seen them in past webinars, and hopefully you'll see them in future webinars, but they did a great job putting this presentation together today, and it's a timely subject, and it must be hitting a nerve for you folks because we've got one of our largest signups approaching 1,000. Hopefully we don't break 1,000. I think the thing breaks down at 1,000, but we got a great number today. So our Hydronics, hopefully everybody's receiving these. If not, there's our web address down at the bottom that you can go and sign up for this. We'll mail these to you twice a year. We come out with an issue. Number 20 should be on the streets as we speak, so hopefully you've received that one. If not, again, let us know or go to the site there and make sure that you are signed up for that. A lot of the slides that Kevin's going to be using and Jody today come out of issue number 11, one that we did a couple of years ago on domestic hot water. It does talk about recirculation in there. Obviously, it's a few years old, so we've got some new product that we're going to show you today that doesn't appear in those pages. So we're going to use some of those past pages as well as Kevin will introduce some new slides and some new products. So Kevin, Jody, it's all yours. Take it away.
Thanks a lot, Bob. You ready, Jody?
Absolutely.
All right, great. Well, we've got Mark in the background too, so this will be a tag team effort. So enter your questions and let us know if you have anything as we go through. So let's begin with the end in mind, and to really understand balancing domestic hot water systems, it's important to first discuss some of the basics, the fundamentals, talk about the design a little bit. So let's start with the purpose. The purpose is to maintain hot water supply target temperature near the fixtures, and this is a nice graphic here showing the water heater supply line coming out and circulating throughout a facility, coming close to the sink, the shower, and another sink, and then this return line is what we're going to talk about today. This return line back to the recirc pump. So nice little graphic there. The point of all this is we don't want to waste water. We really want to minimize that while we're waiting for the hot water to arrive at the fixture. There's a lot of nice articles about this. And in terms of the amount of water wasted, here's an interesting reference from the EPA WaterSense spec you see down below, that the average home waste is over 3,600 gallons of water, 3,650 actually was what they say. So it's just a really, really big number. They also say in that same spec that you should have no more than 0.6 gallons of water delivered to the fixture. And what they're talking about here is between the supply line and the fixture. So this we're going to talk a lot about in terms of the wait time. Here's a really interesting graph. This underscores the importance of water conservation. You can see here the colors, the different shading in the states indicate the gallons per day per person. Like really Nevada really jumps out here as, per person using over 300 gallons. That's just amazing to me. The percentages indicate the projected population change up until 2030. So you can see the heavy users and the ones that are expected to grow the most. Jody, what's going on up here in Maine? You guys don't use very much water, huh?
No, we don't. And actually, if you also look at my other state where I live, Rhode Island, we're also projected for a very low water use growth as well.
Okay, interesting. All right, so time. Another reason that we want to recirc hot water is to reduce the amount of time we have to wait for it to get there. So here's an interesting example. If you just look at a 1-inch pipe, 50 feet in length, and you have a 2 GPM fixture, you're going to wait for over a minute to get hot water from the source to the fixture. And if you look at a low flow fixture, like 0.5 GPM, it's 4 times the amount of time. So we wait for it and we waste a lot of water. So there are a lot of references to this as well. The ASPE design manual says that a wait time greater than 30 seconds is unacceptable. So that's just a reference. And you can look at the IPC, and right now, I guess, Bob, that's 50 feet maximum from the source to the fixture, and it used to be 100. Is that right?
Yeah, that's been sized down a little bit, and I think some other jurisdictions have even shortened it from that. So it's
Yeah.
they realize the importance. The other thing I would add, Kevin, it's not just the water that you're wasting, that you put some heat energy into that water that you're running down the drain until it gets hot enough too. So you got the double whammy there, that you're paying for the water, but you're also paying for the heated water that's going down the drain.
Yeah,
Now,
right.
Kevin,
And I know
now,
that
Kevin,
some
it's-
local codes are more restrictive
Yeah.
than 50
Yeah.
feet. What's that, Jody?
Yeah, now actually, because and you'll find some of the codes actually get even beyond the recirculation side. This week I was in Kansas City. I did a training at the local ASPE chapter, and one of the engineers that deals in some other states, they're actually also dictating how long the dead legs from the recirculation out to the fixture can be from a delivery time standpoint. So everything is really becoming much more controlled.
Okay. Yeah. All right. Let's take a look at an oversimplified schematic. This will just show us some basics that we can understand. Here's a system without recirculation. Whenever a fixture is going to be delivering water, then this cold water supply to the tank makes up for that difference. And as a fixture is consuming water, that flow will obviously come out the supply line and up to the fixture. So say this far fixture was using water, it'd be pulling hot water past, we'll just call this circuit 1 and circuit 2, and all the way out to the end. But when no one is using water, these warm pipes, these hot pipes, will cool down and give up BTUs to the atmosphere, to the ambient temperature. So the problem comes in when there is no water consumption. So what we do, just schematically, is attach return pipes to the far ends of these circuits and bring that water back through a balancing valve, which we'll talk more about in a little bit, back to the tank. So when you look at this and envision that circulator running, it's pushing water out through the circuit, coming back through the valve, and it's actually like a closed loop, similar to actually a hydronic system, like a 2-pipe direct return hydronic system. When you look at this, there are actually 3 parallel circuits here. So the water is also going here, coming back, and it's also going here and coming back. So you can look at this actually as a type of closed system as well. Here's a more detailed and realistic schematic. I like this one. It represents a commercial system with an indirect domestic hot water heater and an electronic mixing valve. So let's talk about this just a little bit. So again, we have the cold water supply coming in. It goes out to the fixtures, which we'll look at on the next slide. That cold water also comes into the inlet of the mixing valve, and of course into the tank to make up any water that's used. Over here are the heat supply pipes. These will come from boiler to provide heat transfer in this heating coil bundle inside the tank to heat the water. Coming out is the hot water into the mixing valve hot water inlet port, and this mixing valve is an electronic controlled valve. This controller right here is an example of a wall-mounted controller, and what that's doing is it's sensing return water. It has control over the recirculation pump. It has control over the modulating actuator in this electronic mixing valve, and this controller also has the ability to change the temperature, the heat supply to the storage. And this schematic represents a type of system that would be used to elevate the system water temperature to a disinfection temperature to prevent the growth of Legionella, which, by the way, is a different topic, and we're not going to get into that too deep here today. We'll be doing another coffee with Caleffi on that topic later, but it has to do with recirculating, so we just wanted to mention that here. Anything else, Bob or Jody, on this slide?
Well, it's a valve that we'll have available, I guess, right, Kevin, later in the year, that EMV, it's called electronic mixing valve?
Yes, this is actually a schematic from the literature from a product that we've been using or selling in Europe for many, many years. It's called Legiomix product, and we are bringing that to North America later this year.
Great, thanks.
So, yeah, we're looking forward to that. So this is the heart of the system. Where does that water go? Let's take a look at, just for example, 4 different risers. So the tempered water comes up this orange line here. It goes out, and we're showing in this schematic a scald protection valve, an ASSE 1070 valve that is used because I mentioned we have, hot water during the disinfection cycle. You have to have protection out here to prevent scalding. So that's why this is in the schematic. And then we're showing here on each distribution leg a balancing valve coming back. So the balancing valves may or may not be located exactly as shown in this picture, but this gives you a good idea of what it looks like out in the circuits, the individual circuits. So when you put those two together, they look like this. And this is a really nice picture. I like this. We're going to come back to this actually at the end of the presentation because it provides a good visual for Q&A. All right, let's look at some of the design considerations. We're going to start, begin at the beginning here and look at the design, and then we'll look at some sizing examples as we go through here. So one of the most important things we want to do is make sure that the recirc piping is getting as close as possible to the fixtures. So these green circles indicate the pipe that are sometimes referred to as dead legs. The longer these are, the longer your wait times are. And if you have long dead legs and your fixture is not consuming water, the water can sit there, and that means there's a potential for bacteria growth in those areas. Another consideration is the pump. We hear a lot about recirc pumps being oversized, so it's a very important part of the whole process. One of the guidelines to keep in mind, this is from the Copper Development Association, is that for hot water, you want to keep your velocity less than 5 feet per second. For cold water, you can go up to 8 feet per second. And these guidelines are really meant to control erosion and noise. You don't want to have too much velocity going through the copper pipes, or you can get pitting and failure. And we actually hear about that quite a bit here in the Caleffi Tech Support Group. Another design consideration here is consider a variable speed pump when you're looking at these recirculation applications. There are a lot of new smart pumps out there. We'll call them smart or variable speed. The larger ones are going to be variable speed pumps. Some of the smaller ones have ECM motors, and there's a lot of new models on the market, right? So here's a picture of one that's installed, and I wanted to put this quote up here that I found in the ASPE CEU 221 document from 2015. So go ahead and read that. I'll give you just a second to read that. So what does OSHA have to say about that? In their technical manual, I found this quote. Now, some people may disagree with that, but it's a good comment that I found in that manual. What do you think, Bob?
Yeah, there seems to be they're not exactly on the same page there, are they? Not a lot of information to substantiate that OSHA statement, other than, maybe, just to make sure there's no dead legs or something out. That's
yeah. So I mean, there's a lot of conversation about that. Some folks are, really concerned about the energy usage of always running a pump. So it may be a little debatable, but I just wanted to put those references up there.
Yeah. The one thing about running the pump, when we look at that from an energy standpoint, though, is if the recirculation and the distribution pipes are adequately insulated, it's an ECM pump, and we're flowing at the right rate, the energy consumption can really be pushed down to a minimum, where that energy is really not a big impact on the overall energy usage of the structure.
Right. Perfect. Yeah, we're going to talk about that a little more too. So another design consideration really gets to the heart of our presentation is balancing. When you have multiple circuits, you have to have a balancing valve and a check valve. So what we've done here is, in this graph, is we've inserted just a schematic of a balancing valve that has a temperature gauge, and this right here is a temperature gauge also. So this makes it really nice because you can see your temperature going out and then your return temperature coming back. So the point of all this is to assure that you have the right amount of flow in each of the circuits to maintain temperature. Really, that's the bottom line of all this. Something else to consider too, and it has to do with what Jody just said, the heat losses in the piping, if it's not insulated, will actually contribute to the cooling load in a building. So I suppose most of the time that's, you know, almost negligible, but it's something to consider. If you have a lot of uninsulated pipe, you may be running your air conditioner more than you need to. All right.
And there was a
Okay, so
Kevin
what
on
we're
that
gonna
slide
do
there.
Yeah.
Can you go back? There was a question about a check valve too, and I see that you've got that up on the upper bullet point there, that the check valve is critical in those when you have those multiple risers.
Right, right. You need that check valve to prevent thermal siphoning back through that pipe.
Thanks.
Right. Any more to say about that, Bob, or is that about sum it
No,
up?
yeah, and I
Okay.
typed in a response too. Thanks.
Good, good. Yeah, you want a check valve there too. So let's do a little exercise. We're going to go through some steps here, and I'll show you some ways to do some calculations. But basically, to design it, what you want to do is to first determine the heat losses in your pipe, and then you can calculate your GPMs in each of the circuits. And once we've done that, we'll look at the head losses and how to calculate the head losses, so you can eventually select your pump. So let's start off with an example. When we say supply piping, here's what we're talking about. From the heat source, these bold red lines, the supply pipe goes out here to that circuit, goes out here to this circuit, and out here to this circuit. So we're going to calculate the BTUs per hour that are transferred from the hot pipe to atmosphere. So the flow rate that you need in each of these circuits is based on the heat loss that I just described. So we'll look at that. Now, if you can imagine, if you had a long run or a non-insulated pipe, it's going to give up a lot more BTUs than if you had a well-insulated pipe that was shorter distance. And that calculation will determine how many GPM you need on your recirc pump. Here's a little chart. Look in the lower right-hand corner. This is a stark example of uninsulated versus insulated pipe. Look at that 1-inch pipe. An uninsulated pipe is almost 8 times greater in terms of heat loss than an insulated pipe. And this chart does use a 99-degree difference. And what that means is between the water temperature and the ambient temperature, if you had that much delta, then the numbers below would represent the BTUs per hour per foot of pipe. And that 2-inch, 136 compared to 15, that's 9 times. So obviously it's critically important to have the pipes insulated. And Bob, aren't there some areas that actually are requiring insulation on the recirc piping? I've read that. I'm not sure if that's national or if that's more of a local.
Yeah, and another point that Jim just typed in, he said, talking to Jody's point there about constant recirculation, he said it's pretty rare to see a recirculation loop completely insulated with 2 to 3 inches of insulation like the tank might be. So there, and I think your next slide actually has one of Siegenthaler's calculators that you can put in the thickness of the insulation and play around with that and see how 1/2 inch to 1 inch changes the heat loss. So just to answer his question too, but yeah, I mean, I would think that the insulation standard should be written in the certainly in the spec that the engineer does on what they want either by code or what they recommend for the design. That's a big number on a large building.
It's a big, definitely a big number.
Yep.
So again,
now, Kevin, one other.
Yeah, go ahead.
Yeah. Now, from this, I'm not sure if you're going to jump off this one right now, but something really to take away from this, and we run across this with a lot with hydronic guys designing recirc systems. They think you got to calculate for the entire loop. And I like your drawing with the red lines up there because realistically, the heat loss is only important until you get to that last fixture. As far as water delivery, whatever losses happen on the recirc line really don't play into the purpose of that recirculation piping.
Exactly. Yeah, good point. Thanks for bringing that up. Okay. And the ASPE Plumbing Engineering Design Handbook has a lot of great information. It has all this information in there, so we highly recommend you check that out. Okay, let's look at an example. Again, we're going to go back to this oversimplified diagram. So I'm not showing any mixing valves. We're just breaking it down to the most basic elements. So what we're going to do is calculate the heat loss in this first section. So it's at the outlet up to the end of this first circuit. We'll call that circuit number 1. Okay, so let's for our example assume that we have 100 feet of non-insulated 1.5-inch copper. All right.
Some feedback there.
A little bit of feedback. Make sure you're muted. So in that 100-foot 1.5-inch copper line, let's look at some numbers. Let's say we have 140-degree water coming out of that storage tank, and we have a 72-degree ambient room. That makes it convenient because that's a difference of 68 degrees. And this curve I found in Engineering Toolbox has this red curve right here that we're going to look at. So this is just one reference. There are lots of tables that tell you BTUs per hour per foot. So this is just one reference that I found that we'll use. Okay, so if we look at the 1.5-inch pipe, we come up to the red line and come across, we see that's about 75 BTUs per hour per foot of pipe heat loss. Somebody needs to mute. Okay, so if we take that 75 and multiply it by the 100 foot of 1.5-inch copper, we're losing 7,500 BTUs per hour in this section of supply piping. Does it make sense? All right, now let's take that a step further and look at a 3-circuit system. And we'll plug in some design temperatures. Let's put some numbers in here. 140 degrees coming out of the storage tank. Let's assume a 10-degree delta T between the supply and at the end of our circuits, and a final temperature coming back to the tank of 120. And by the way, this is the equation that you use to determine GPM. So we'll take the BTUs per hour using our delta T of 10, that becomes BTUs per hour over 5,000. So that's the basis of our equation. So if you remember, oh yeah, here's a note. Another note from OSHA technical manual suggests storing at 140 degrees. So it's just kind of a handy reference. So that lines up with our example here. All right, if you remember from the last slide, we came up with 7,500 BTUs per hour lost in that first circuit. So if we divide that by 5,000, our circuit number 1 should have 1.5 GPM flowing through it to deliver the amount of water that we need to maintain 130 degrees out at the end of the circuit. Let's say for circuit number 2, it's a little longer. Let's call that 120 feet of 1.25-inch copper. So we're dropping down 1 pipe size for circuit 2. And if we plug those numbers into the previous slide, we come up with 7,800 BTUs per hour, which results in 1.6 GPM in that line. You can see where we're going here. So the third circuit, let's say that's 120 feet also of 1-inch copper. For example, the result of that one is 1.3 GPM. So these are the GPMs that we need in each of those circuits. And these are the GPMs that you would use to size your balancing valve. So that's what that involves. To get your total, you add them all up. So in this example, we have a GPM requirement total of 4.4. Any thoughts or questions about that, guys?
Yeah, one of the things that I run across a lot with engineers when I'm visiting and talking about recirculation is about how to choose that delta T. You know, one that I've heard recently is a lot of guys will say, you know, my heat loss from the tank to the last fixture, I want to minimize that to a 5-degree difference. You know, if you look at that formula, basically to drop from a 10-degree drop to a 5-degree drop, you are essentially doubling the amount of flow required to balance it out. So realistically, when you make that kind of decision, it may tighten that band up, but on the flip side, I now have to move more water, which will equate to possibly more friction loss in my pipe and possibly a larger pump to deliver the hot water out to that last fixture.
Right, right. And another point, in this example, I'm just assuming we have 140 all the way across in this horizontal line, but realistically, you're going to lose a little bit of temperature as you move down this main supply pipe too. So just for simplicity, I just kept this the same. But if this is a really long run, you may end up with 135 degrees down here at this last T. So that's just the math to show you how to do that. Okay.
Kevin, a couple comments that came in, it's a good slide to put them on there, that for energy conservation standards, one of the attendees noted that loss needs to be put in the HVAC calculation too to get your energy standard. So, that's part of the loss. And then somebody asked about an expansion tank on the system. Again, these are simplified drawings. Obviously, if there's checks somewhere in this system, there needs to be a thermal expansion tank, which that's a good thing to make note of. We're not, admitting that, or omitting that, I should say. It's just trying to keep the drawings as clean as possible. So, what else?
Yeah, great comments. Yeah, send in your comments. We love to get those comments. It helps all of us, and we'll share that information as we go.
Yeah, and I don't mean to break in on Kevin all the time, but sometimes it's easier to answer questions we're on the slide because we get to the end and we lost track of where you had asked the question. Right. So hopefully this is working out. Right. Thanks, Kevin, for accommodating.
Okay, so step one was determining GPM. We just went through that. Step two, we have to look at the piping head losses. What we're going to do in this example is we're going to look at the circuit with the most head loss. And I'm just going to, for simplicity, assume that this longest one, circuit number 3, has the most head loss. But just remember, it's not always obvious depending on your piping. And, so when we do this, if we assume circuit 3 has the most head loss, once we get everything balanced, if we balance circuit 2 and circuit 1, then they'll be about the same too. And by the way, looking at the circuit with the most head loss is not the only way to do this. I'll talk about that here in just a second. So we're going to look at the whole circuit. So this first section, let's put in a number of 40 feet from the supply to this point right here. So this green line, we're going to look at this whole thing. So let's say that we talked about that being a 1.5-inch pipe. The second segment over to circuit 2, from circuit 1 to circuit 2, let's call that 50 feet of 1.25 inch. Let's call this third leg 75 feet of 1 inch. Again, we're reducing in size. And let's plug in 165 feet of 3/4 inch for this return and see how the math works out. So I just assume that the return is going to be the same length as all 3 of those supply lines. And I mentioned too that there are other ways to look at this. You can consider them to be parallel circuits, and that's a kind of a complicated calculation, but Idronics 16 talks about that. And some engineers prefer to just look at the head loss and only the return from the longest run. And that's also valid. So there are different ways to do it, and you'll see what I mean here in just a minute when we go through the example. And by the way, use whatever tool you use for your piping loss calculations. We'll show you one in the example, but there are other sources, including the ASPE data book that has all this information in there. So I'm using, for this example, a tool, hydronicpros.com has a tool that determines equivalent length of pipe. And if you remember, we looked at that first leg being 40 feet. So I put in 40 feet of 1.5-inch copper. I put in a couple of elbows, a couple of T's, and said it was soldered. So the equivalent length of pipe comes out to be 49.6 feet. So you need to calculate the equivalent length of pipe based on the architecture of your piping system. And we're going to use that 49.6 feet and multiply that by the head loss per foot And this is a table I found in Engineering Toolbox. Again, there are other references that will tell you pressure drop per length of different types of pipe and tubing. So here's a table that's 1.5 inches. We'll look at the pressure drop PSI per foot and pick the closest GPM that's in the table. This is approximate, but it's going to get us close enough. So if you take the 49.6 times 0.001, you get 0.05 PSI loss. Divide that by 0.433 to get feet of head. And here's a 0.12 feet of head. So that's the head loss in that first 40-foot, 1.5 inch section of pipe. We do the same thing for the second section. If you remember, it's 1.25 inch pipe, 50 feet, and go through the same calculation. Here we go, 1.25 inches. We came up with 57.2 equivalent feet, and the math gives us 0.53 feet of head loss in that second section. The third section is that 75-foot piece of 1-inch pipe. So the resultant calculation is 0.94 feet of head loss in that section of pipe. Now the return line, this is where it gets interesting. If you remember, we estimated 165 feet. And this time I put in, a couple more elbows. I put in 6 elbows. And this is important. I put in that there's a globe valve in that line. Now what I'm doing here is I'm just simulating that balancing valve. If you remember, there's a balancing valve in that last return line, so you have to account for it. Now, and you'll also see here I put in a check valve. Another way to do that is to just look at the piping and then look at the pressure drop across the valve that you're going to use and determine the head loss across your specific balancing valve. You can do that too. This is just a simple way of accounting for that balancing valve in that pipe. So look at the head loss in the return, 10.3 feet of head. It's really significant compared to all that supply piping. And here's what that looks like. So we had 0.12, 0.53, 0.94, and then 10.3 coming back. You can see there that why some designers would say, I'm just going to look at the return pipe from the furthest circuit, because that's, in this example, it's 10 times any of the other ones. So to get close, that's a legitimate approach. So in our example, we came up with a sum total of 11.9 feet of head. Okay, so now we have our GPM, we have our head losses, and here are a couple of examples of pump curves. We're not going to get into this too deep. I just wanted to show you that that's where you end up in sizing and selecting your pump. Any more questions on this section before we shift gears and look at balancing, Bob or Jody?
Yeah, there was one thing I think it's a little bit out of our technical range here, is about bacterial growth in copper as opposed to using a PEX or plastic pipe. I guess that would be something for the CDA, the Copper Development Association, to comment on the difference between copper plastic for bacteria growth. And then somebody asked you any time that you'd use a 1/2 inch return, and certainly you would. He said it would keep the flow velocity down to 3 feet per second. Maybe he's referring to that one example back a couple. I didn't quite keep up with the other questions in the slide numbers here, but yeah, I mean, the key there is the pipe size is sized for the velocity that you want to go through it. If you want to, size the pipe down, and it would add some pressure drop to the system. So you have to balance the pressure drop by sizing smaller as opposed to the, the flow rate that you're trying to get through it.
Right. Yeah. Great question, because you could just go back and run that 165 feet in a 1/2 inch copper pipe and see what it comes out with. You may end up needing a bigger pump. You may have too high velocities. That's true.
Yeah, that's why we're giving you the tools to figure all that stuff out. These formulas here, you could run your own examples on. In fact, you go back to our examples and run them with different pipe size. We're just kind of pointing you to the tools and what the industry is kind of suggesting for this design here too. All right, thanks.
Right. So we looked at our heat loss. We eventually came to the point of selecting our pump. So we'll switch gears just a little bit here and now talk about balancing, which is really, really important.
Hey, Kevin.
As we know, yes. Hey, Mark.
Kevin, this is Mark. I'm going to chime in on that last question about 1/2 inch. And obviously downsizing a balancing valve to a 1/2 inch from 3/4, there's some material savings there, right? So that's on the positive side. On the negative side, of course, is that you're now restricting your return circuit, so you're going to have more pressure drop, which is going to require a higher head pump and probably more energy consumption over the life of the installation. And the second thing too is that you have higher pipe velocities as well associated with the smaller balancing valves. And the higher the temperature in your return leg, the lower you want to keep that pipe velocity, as you showed in the earlier slide. So those are the trade-offs. As long as you can keep that pipe velocity below an acceptable level for that temperature, and as long as you have acceptable head loss in your pump, then 1/2 inch would be acceptable. But just to let everyone out there know, the vast majority of balancing valves that Caleffi sells for hot water recirc is 3/4 inch size by far.
Right. Yeah, that seems to be the size that's most often used. Yeah. Okay, let's switch gears and get into balancing. Here's a diagram of a circuit that doesn't have any balancing valves in it, and of course water will take the path of least resistance, right? So you might have 1 GPM here close to the supply, dropping down to 1/2, and then maybe in a further circuit only a trickle, and so the furthest circuit is going to be starved, and the closer ones will get short cycled. Now, the problem to overcoming this is not by putting in a bigger pump. What you have to do is you have to balance these circuits. And again, I think I mentioned this before, but this is the point. We've got to achieve optimum flow to maintain the temperatures that we want at those fixtures. So this is not an easy thing to do. Balancing just in itself is pretty difficult, and let's talk about that a little bit. So what I want to do right now is throw out a poll question, and I want all the attendees to tell me, what's the biggest challenge you face in working with domestic hot water balancing valves? Woody, we ready to go on that?
Yep. So let's take a look at this question. So why is the biggest challenge you face in working with domestic hot water balancing valves? Is it difficulty in knowing what type balancing valve is best? Difficulty in knowing what size balancing valve is best? Being able to accurately set balancing valve flow rates? Difficulty in sizing circulator? Or maintaining low pump electrical consumption? So those are our 5 choices. Let's think about it for a couple of seconds. Woody, when you feel that it looks like we're pretty much everybody's had an opportunity, close it out. All right, so it appears, well, at 58%, being able to accurately set balancing valve flow rates. And I think from our aspect, I would say that is probably right on line with what we're seeing. Would you not say, Kevin?
Yes, that's what we're hearing.
Yep.
Yeah.
So thanks for the poll, and I think we'll continue onward.
Okay, so let's talk about that a little bit. Where is the difficulty? It's not easy. We know that. Some reasons are it takes time, especially if you use a traditional manual balancing valve. These valves are, we're going to get into a little more detail, but they take a while. And what you have to do is set it for a given differential pressure to determine a given GPM. And system conditions are dynamic as things change, as fixtures open, fixtures close, as temperatures change, the pressures in the circuits change, and so it's all interactive and it's dynamic. So setting a manual balancing valve is an iterative process. There's just no way around it. It takes quite a bit of work, and you have to set it, come back, maybe adjust another circuit, set it and come back. So that's one reason why this is not an easy thing to do. You know, realistically too, it's one of the last things to be done on a project. So you know how that goes when you get close to the end of a project. It's things get rushed, and that's one other contributing factor. So, all right, let's talk about valves. There are a lot to choose from. You know, and we're going to talk about each type of valve, well, the three main types of categories. And here you can see some various models that are available out there. Let's start with a second poll question. This is my last poll question, folks. So we want to hear from you on this one.
So, which type of balancing valve do you prefer or have the most experience with? Is it a manual valve, also referred to as a pressure dependent or a static valve, an automatic, also known as a pressure independent or a dynamic, a thermal or a thermostatic valve, or do you not have a preference? And the winner is manual with 36%, with automatic coming in at 25%. And interestingly enough, thermostatic came in 23%. From those numbers, and I think from the discussion Kevin's going to drive us into next, I'd probably say that with the manuals, it's probably, when we look at things from an availability and a price structure, that the manual, there's a lot of reasons why that manual does end up on top. So with that, I'm going to hand it back over to Kevin.
Yeah, thanks. Okay, let's start with the manual valve. These are the most common. They've been around forever, and typically they are the lowest product cost. So everybody's familiar with these. Some of the main points regarding manual valves is, as I mentioned, the flow will vary with pressure changes. Okay, they are called pressure dependent valves because the flow will change anytime the differential pressure changes. And I mentioned before that the labor that's involved in the iterative process of getting these guys set just right.
Yeah, Kevin.
So,
also with the manual style valve, I do like to talk about that significant labor because one of the significant things or the key things about the manual valves is if I have a series of these valves, because of their static nature, the valve really can't be adjusted once and walked away from, because every time I adjust another one of the valves, because of that pressure dependent nature, the minute I change another valve, the conditions in the system change, and I actually have to go back. I should be going back and verifying or possibly readjusting every other valve at the end of the process, which, to Kevin's point, really drives the labor up.
Right. So there are basically two types. Well, there's a third type we'll get to too, but a variable orifice valve. Let me tell you what I'm talking about here. Here are the two plugs where you hook up a differential pressure tool. And in a variable orifice valve, when you make the adjustment on the valve, it actually changes the CV, or the valve opening, in between the two pressure pickups. That's why it's called a variable orifice valve. Now, these, besides being generally lower cost type valves, they're pretty good for low flow actually, because when you crank the adjustment down, you get a good high differential between these two ports that's readable. So that's a pretty good reason to use these when you have very, very low flow. Let's look at a fixed orifice type. Here's a picture of one, and the pressure pickups here, the PT ports, in between those two is a venturi, a fixed reduction in cross-sectional area that does not change when you adjust the valve. So as you adjust this section of the valve to open and close the main port inside the valve, the cross-sectional area or the orifice doesn't change. That's why it's called a fixed orifice. So these are a little quicker to set up, because every time you make an adjustment, you're not changing the CV where you're measuring your differential pressure. Okay, so they can be a little quicker. That's a fixed orifice type of valve. Either one requires a commissioning tool, and any balancing valve that has two pressure ports requires a tool like this one or something similar. And you hook up the tubes, measure the differential pressure, and convert that to GPM. So your ultimate goal is to read your GPM and try and get that close to what your design GPM was that we calculated a little while ago, if you remember that. So depending on the product, some products use a tool like this, where you have like a rotary slide rule type of device that matches up with the brand of the valve. There are some digital types of differential pressure tools, and then many of them have graphs like this. Like the Caleffi 142 series has graphs like this. So on the right here is where we're measuring our differential pressure. So on our DP tool, we would measure the differential pressure and come across to the position of the valve adjustment and come down. And what you have to do is try and change the valve position and reread the pressure until you settle in on the GPM that you want. So that's where this iterative process comes in. So the valve adjustment position is represented by these different curves. So that's one way that you set up a manual valve. Now, there's a very unique manual valve on the market, and we really like this one. It's our 132 quick setter. It's a manual valve, okay, but it has a built-in flow meter. It gives you local indication. You don't use any charts or slide rules. The way to adjust it, if you look at this diagram down here, is you pull this little pin, which sends some bypass flow through the flow meter. You adjust the valve here and zero in on your GPM and let it go, and you're done. So it really simplifies and speeds up the process of balancing your system using a manual balancing valve. Any more on that one, guys? So,
Hey, Kevin.
Yes, Mark.
Yeah, just there's a question that came in concerning the minimum flow rate that could be attainable on a manual balancing valve. And it's a good question because as designers do their calculations on heat loss and the resulting flow rate that they want in their recirculation loops, oftentimes they're below 1 gallon per minute, a half a gallon per minute, 3/4 of a gallon per minute. And so, the answer to the question is a half gallon per minute. These valves, as an example that you're seeing here, the minimum flow rate on that scale starts at 1/2 gallon per minute, and it's a very common flow rate that is specified for hot water recirc.
Right. The scale in this picture is one of the scales. The other scale is 0.5 to 1.75 on these. So that's the one that sells mostly into the domestic hot water recirc. So, all right. Let's switch gears and look at automatic, also pressure independent or dynamic valves. Now these are different. They have a cartridge that's inside the valve body that delivers a constant GPM. So if you are sure that the GPM specified is what you want and there's not a lot of doubt about having to change that, these are great products. You don't have to balance them, you just install them and forget them, and they're nice and compact, so they're really popular. A lot of customers really gravitate towards these. Now internally, if you look, what this is as the fluid enters the valve body, it pushes on this cartridge, which has an opposing spring inside. The more fluid thrust comes in here, the more that spring compresses, and it tends to close off the bypass port. And what that looks like graphically is when you have very little flow or little, low fluid thrust coming into the valve, your flow will come up to the point at which your cartridge is designed. For example, you might have a 0.5 cartridge or a 1.5 cartridge. And when that differential gets to that point, the spring will start to compress. And from there on in, through the range of the spring compression, it will maintain a constant GPM. And once that spring gets completely compressed, then the valve can't shut off anymore, and you can have an increase in flow. But over the normal working range, these types of products maintain a constant GPM. So that's a fixed flow, and as you can imagine, it's just looking at flow. It doesn't have any response or know anything about the temperature in the recirc line, which brings me to thermal balancing valves. Now, this is a picture of a brand new Caleffi product called a thermosetter, and it's specifically designed for domestic hot water recirculation. It's not a valve that was once used in hydronics and then built in low lead for plumbing. It's designed specifically to do what it does. The unique thing about this valve is that it modulates flow based on temperature across that thermostat. So I like to think of it as a temperature solution for a temperature application. and it responds to the supply temperature changes as well in the water coming down the pipe. This product has actually been sold in Europe for many, many years under a different look. This is the next generation of the 116, but it's been around for a long time, so it's a nice proven technology. Another way to think about it is it delivers the flow that you need to provide the right temperature. It doesn't deliver a calculated flow like a manual or a dynamic balancing valve. So in that way, it's different. This particular model has an adjustable temperature set point, so that's a competitive advantage compared to some of the other thermal balancing valves on the market. This one you can see on the knob just has an adjustment. It looks a lot like a mixing valve adjustment. And they're really good for retrofit. If you don't know the flow rate, if you don't know what's going on in the system and you want to put in balancing valves, like this picture here, you can see a couple of these installed. This was definitely a retrofit. You can see these large plastic pipes, and so they cut in, put in some isolation ball valve, put in the balancing valve, and put in the check valve, which we mentioned earlier too, and then another isolating ball valve. So that's a good shot of a retrofit. Just to drill down a little bit more on this product, this kind of comes in three models. The basic model has just this cartridge right here and a cap for this second part of the body. It's just basic. It does balancing only. But where this product really stands out and is totally unique is that you can get another cartridge that goes in this center section here, either a thermostatically activated cartridge or a remote control bypass valve. What these do is they bypass the flow. They open a special passage I'll show you about and bypass the balancing cartridge if you want to do thermal disinfection process in the recirc line. And we'll show you a little bit more about that here in a second. And the cool thing about this too is this can be all converted in the field. If a customer installed a bunch of these with just the plain cap and then wanted to do thermal disinfection later, you can come by and screw one of these cartridges in without removing the valve body from the piping. And by the way, all the cartridges can be unscrewed and removed and cleaned and replaced if need be. So that's really nice for maintenance. A little more about the valve. Here's the balancing only version I talked about. So here's a thermostat that moves linearly up and down in this body cavity, opposing a spring, and the valve seat right here opens and closes based on the linear movement of the valve. As the temperature drops, this will contract to open the seat and allow increased flow. It never closes fully. Even at the highest temperature, it still has a minimum flow. You always have to have water flowing across that thermostat so the valve can respond. Secondly, now here's if we add that thermal bypass cartridge. What happens here is when that cartridge sees 160-degree water, it knows that the system is going into disinfection mode, and it opens up a special bypass port to allow more flow through the valve for the process of thermal disinfection. And the remote control one is a 24-volt on-off spring return actuator. It's the same actuator that's used on the manifolds that we sell and the zone valves. And this gives you the ability to tie all of your recirc balancing valves into a building automation system and open and close them whenever you need to, or whenever the building automation system wants to do thermal disinfection. So to kind of sum it up with this valve, it's a self-balancing valve, automatically adapts to changing conditions, and back to this basic circuit. As conditions change, each one of these opens and closes. They change the flow in the circuit, and when they do that, they will allow the other circuits to take advantage of the increased differential, and it all self-balances out. Now, the really cool part about this is what you want to do is combine this with a variable speed pump, one of these smart circulators we talked about. And in conversations we've had among our engineering group, we think that running a variable speed circulator in delta P mode makes sense. If the circulator is taking care of the delta P in the system, and these thermal balancing valves are taking care of the temperature in the system, then they're working together in harmony to make sure everything is working well. So bottom line on this valve, it saves energy. The pump will slow down when the valves are at minimum position. When they're all at set point and the valves are closed down to minimum, the pump can slow down and just coast and draw a few watts. So if your pipes are all insulated and you use a smart pump and this type of balancing valve, you can really get some great energy savings. So
also the other way the valve definitely will save is on the installation, in that when the valve's installed, all you have to do is make a temperature setting change on the valve to whatever you want that water temperature at that location to be, without the iterative process of setting up, say, a manual balancing valve.
Right. And this particular schematic shows the balancing valves with that 24-volt actuator on it, but that's just a schematic.
Hey, Kevin.
Yes, Mark.
It's interesting to point out before we leave the schematic, there's different jurisdictions around North America that require a certain temperature returning back into the hot water heater. For example, one of our listeners pointed out up in Canada, it's 131 degrees Fahrenheit. And so with a mechanical balancing valve, of course, attaining that requires some very accurate calculation and perhaps some field adjustment after the calculation, the theoretical calculation, to attain that 131. What's unique about the thermal balancing valve, and it's the same for us when we apply it in Europe, is that in those locations where you have to have a certain temperature, design temperature, coming back to a certain part of your system, in this case, the return side back into the hot water heater, you can make sure you accurately accomplish that by simply setting the valve to that temperature. So these are actually really good valves for maintaining conformance to that code requirement or to that building code requirement, for example. So it's an interesting question or point that came in, and this was a good part of the schematic to point that out.
Yeah, that's
and another good point on that, Mark, also is, if you look at this drawing here, it does show the balancing valves close to the return on the tank, which would allow for that. The next slide that Kevin's going to put up are going to show them up at point of use. So one of the things that is going to be, I think, dictated on where the location is going to be what's the important temperature I'm trying to maintain. When I look at how we have it here, it's nice from the aspect of this. If I'm trying to maintain the temperature at that last fixture, if I put the balancing valve, the thermal setter at that point, I just know I need to achieve 130 degrees here. I set it to 130. Whereas if I put it down in the mechanical room, I then have to calculate for the losses in my return line to figure out my setting.
Right. Well, this is the last slide. We have, I think, we're right at 1 o'clock. But if we have any important questions, if anybody wants to stick around, we'll stick around for a few more minutes. Jody or Mark, is there anything else that came in that we could address right now?
I got a couple of simple ones that'll go quick. The size available on the 116, Kevin. Eric was asking about that. Half through.
If you're going to do a manual sizing calculation on the 116, the literature, and by the way, that's up on our website, the literature shows a curve called the CV design. And in that curve, the design CV is what you want to use if you're calculating the head loss across the valve. So just check out that curve based on your GPM, and that'll give you the head loss.
Bob, if he's looking for the physical size, it's a 1/2 inch and 3/4.
Okay. I got a couple more if you want me to keep going here.
Yeah, sure. Go ahead.
The check valves are options on the 132 and the 127. We have a tailpiece with a check valve in it, correct?
Right. And the 116 also has a check valve option. You can screw it into the outlet.
Okay. All right. Let's see.
Hey, Bob and Kevin, maybe it's good to, there's a number of questions that came on the location. Where should the check valve be placed in the circuit? And I mean, it could suffice in either the supply side or the return side, but typically on the return side, and it's really meant to prevent that ghost flow, if you will, during non-flow conditions, so you don't have this drain of heat from your hot water tank. It really doesn't serve as much of a purpose when you're actually circulating. So just a little note on the use of on check valves. And some of our balancing valves, by the way, another question that came in is do your balancing valves for hot water recirc contain built-in check valves? And the answer to that question is in the case of the quick setting balancing valve that you saw, the 132, that does come with check valves as an option built into it to prevent thermal siphoning. And in the case of the newer valve that Kevin went through, the 116 thermal balancing valve, a check is an option that you can add on to the valve.
Yes, and in our new version of the 127, the FlowCal Plus, that one has a check valve built in also. Okay.
Actually, Kevin, one point for clarification that I think we probably should make, because I kind of realized this as we were going through, because we are a little bit, let's call it thermal balancing valve focused. If I'm doing an ECM circulator, I'm probably going to run it in a delta P mode with that specific balancing valve. When I shift over to, say, a static balancing valve, I would probably be running in a delta T or a T mode to control that return water temperature and utilize the variable speed function. You know, so that does change with the style of it. But you know, part of a lot of our discussion when we're doing our lead up to this was about the 116 valve, and that's how we kind of got into the delta P column of the operation.
Right here. Okay. So the question is about check valve placement. Why can't the check valve that's located inside of the circulator suffice to prevent any thermal siphoning in your hot water recirc system?
Jody or Bob, you want to take that one? I'm looking at this picture.
Well, Kevin, I can take that, because the journey of the hot water will not, basically what you're doing is short cycling your hot water. Let's see here, up through the secondary side of your system and not going through your primary side of your system through the pump. And maybe this wasn't the best diagram to show that. We perhaps could show another one and send that out to everybody.
I think what you're getting at is you could have flow going up the other side of the line. Is that what you're trying to say? If you had a loop, it could go up, even though the pump was checked, you can get a thermal heat transfer up the other side of the loop.
That's correct.
So a check valve at every setter in this picture here would be the best way to you know, eliminate that potential.
Yes.
I think I'm reading that right. It's sometimes hard to read the question, understand exactly what they're asking, but I think that's the correct answer. If not, we're going to respond to these two, of course, offline. But and if the pump people want to chime in on that, certainly we'd love to hear from them. I know Kevin, some other people are online that are pump experts.
Another point to, I think, not clarify, but to say right here on this schematic is, why use a thermal balancing valve versus a mechanical balancing valve, which the survey indicated most people have been using up until now? Well, first of all, they are certainly very easy to balance. You just set it and really kind of let them do their thing, because they are a modulating valve, as Kevin pointed out, and they'll modulate down to the temperature that you got set for that riser. But the other thing they do is they minimize electrical consumption when they're married with a variable speed pump. And why is that? Well, the dynamic conditions in your hot water system, well, they're dynamic. Your design considerations are usually done under a static situation, but you do have changing conditions. So for example, if on that further right leg there, if there was a demand on that, let's say those floors, that riser has a demand for hot water is going to come racing through the supply header up to that circuit, and resultingly, you're going to have much less heat loss than your calculated heat loss in that circuit. So if you had mechanical balancing valves under that condition, you would have higher temperature water going through, returning back at a higher flow rate. But because a thermal balancing valve will sense exactly what temperature is coming through there, and it says, okay, it's starting to get warm here. I want 120. It's starting to creep up to 121 or 122. It modulates down, lowering the flow in that leg, which causes the temperature to get back to 120. And the pump senses that closing down as an increase in head. And by operating under a variable speed or auto adapt type mode, it will slow down and minimize the electrical consumption of that pump. And taken over the lifetime of the system, that adds up to some huge electrical savings. And thus, another big benefit is the savings of this balancing valve and hot water recirc. And the survey had indicated it wasn't the top result from guys that responded, but it was up there in terms of pump electrical costs being a concern with domestic hot water balancing.
Right. Perfect. Any more, Bob?
A question came on low lead.
Yeah, I think I answered that, I think online, that we are low lead. I mean, some of our valve, like the quick setter, comes in a leaded version for hydronic, but the quick setter plus is the low lead version, comes with the temperature gauge as well as a check valve in it. So I think every balancing valve we offer is available in the low lead, right, Kevin?
Yeah, you were breaking up a little bit there, Bob. Yeah, the quick setter plus is the low lead version with the built-in check valve and temperature gauge option.
Yeah,
That answer
it's
the question?
available. Yeah. It's available both ways, but all the other balancing valves are low lead that you talked about.
Yes.
Okay, and then let's see.
Another question came in on the placement of these balancing valves. We showed them here on the return side of the hot water circuits. The question, I think, is why would you not consider placing them on the supply side of the circuit?
So the thing with placing them on the supply side of the circuit, now you're making an adjustment here for a very low flow rate, whereas on the supply side, when I have 100% demand on the domestic water side, I may have a supply leg that's trying to flow at 100 GPM. So it really is not a location that you can adequately control your recirculation line because of the system demands, if I put it on the supply side.
Yep.
There was some points about insulation, and I think we showed a photograph or two of hot water recirculation systems with bare pipe. And so we're not recommending that be done because there's a lot of heat loss there, right? As Kevin, you pointed out, perhaps those photographs were taken prior to the contractor buttoning them up with insulation. You certainly would want to insulate your hot water recirc system, just as you would insulating your hydronic system.
Here's one question, Kevin, maybe you know, on the 116 that Kevin Hay asked, does the thermal balancing valve always allow a minimum flow for the 160-degree thermal disinfection feature to operate? So I guess what he's asking.
It has a minimum, it never closes fully.
Okay. And in the 160 mode, does it go wide open when it senses that 160 with the additional thermostatic cartridge? The one there you go.
Bob's looking. Yeah. While Kevin's looking for the picture, and the thermal disinfection, there actually has a CV. I forget what the numbers. I don't have the chart in front of me. Somewhere between the fully open and the almost fully closed position. I know, Kevin. Do you remember what that CV is? The thermal disinfection CV.
Yeah, the thermal disinfection CV is about halfway between the full open and minimum.
Yeah, I think that answers the question. If not, Kevin, ask us for more detail, but I think that's exactly what he was asking. I think we're pretty good. I mean, like I say, we answered, you probably heard me type in there until I muted. Sorry about that, everybody. But I think we got to quite a few, but Kevin will, and Jody and I will get back to the ones that we didn't get to. I see there's still quite a few people on, but they're starting to peel off now. So I think if everybody else is fine from the team, I guess we'll call this a wrap. Great job, by the way, Kevin and Jody. This was good information. It was well presented, and sorry about some of the technical glitches, but we're getting better.
Well, Kevin deserves all the credit. I really just kind of rode along in the sidecar, so.
Did the heavy lifting.
Well, thanks everybody. Thanks very much, Bob. Thanks, Mark and Jody. And you know how to reach us, so let us know what your questions are, and we'll talk to you next time. Bye-bye, everybody.
Thanks.